Hey, welcome to Hackers Teaching Hackers CTF 2021 Solve videos. This video, we're going to be taking a look at the fifth and final crypto challenge. So let's go ahead and take a look. In this crypto challenge, it's called Session Keys. There's some story information about this one. Ended up being, I think, a little difficult because nobody solved it. So something we'll keep into account next CTF. So for this one, we're given session keys. I already have this local and I have it local in here. So I'm going to show you what that looks like in a second. This is from the last video. So let's go ahead and connect to this one. It says Nexus Cryptographic Service. If I type in A, it's invalid input. If I type in something else, I keep getting invalid input. So let's go see what's going on. This is the actual service that's running on the back end. So the flag has been sanitized when we get to the user, but obviously it's populated on the back end. This one is 28 characters. If I highlight all of the question marks and look down here, it says 28 selected. So 28 characters. We have a generate key function, an encrypt function, a check user input, and then a main. So when main runs, it's going to print out this information, and then it's going to ask us for input, or ask the user for input. It doesn't actually prompt them at all. You just have to know what to type in. It's going to collect that input and then pass it to check user input. From here, if that input is encrypted flag, it's going to encrypt the flag from up here, encrypt, and send it back to the user. If it's anything else, it's going to see if it can go from hex byte. So it's going to see if you have valid hex text, it's going to convert it and send it, encrypt it, and send it back to you. If you don't, anything else is going to do invalid input. So let's try to give it valid hex text. 41 is a capital A, so let's send it, and it gives us back information. And this runs in a constant loop like a REPL. So it's constantly asking, and if I keep adding 41s, it's going to keep encrypting it. So what actually happens? How does this encrypt it? It's actually just encoding it. We'll see how this works. We are using hashlib, but all we're going to do is we're going to take the SHA-256 of this key, and then what we're going to end up doing, let's follow the whole chain here just so we can kind of see what's going on. In the main function, we take the user input, pass it to check input. From there, if it's encrypted flag, we'll encrypt the flag and send it back to the user. So let's do that. Do this, encrypted flag. Here is our encrypted flag. We want to somehow get the non-encrypted version from that. So we can go ahead and send another input with some data. What it's going to end up doing is saying to encrypt that data. So here it's going to generate a key. What it's going to do is it's going to take the current time and put it in here. It's going to convert that to a sort of session key or an intermediate key. And then it's going to SHA-256 that. I think a second ago I might have said that this was the SHA-256 of the flag, so I was wrong. So it's going to take the current time on the server and convert that to a hash or hash it. Then that comes back here, and then what it's going to do is it's going to go through our input, which is B, check to see if it is longer than the actual key. It's going to tell us your message too long, right? So it has to be the size of the SHA-256 hash. From that point on, it's going to enumerate or go over the number of bytes that are in the input that we have. And for each one, so let's see, we're looking at the first character in the input. It's going to take the first character, the first byte of the SHA-256, and it's going to XOR it. And it's going to continue to do that. The second byte gets the second byte of the key, and they get XORed together. And it keeps doing this over and over again, and then finally returns the hex value of that to the user. So when I go over here, what I can do, if I type in 41, whatever that timestamp is of 41 ends up being the actual flag to this. So what's the trick in this problem? The trick in this problem is that we're using essentially a session key. Every time I connect, there's a new key that gets generated by time. But what happens if I can connect more than once per second? Right? I can actually get the encrypted flag with the key and then guess my input and then go from there. So it turns out that I can work on this really, really fast in a tight loop and cause one request to get the encrypted flag, which will give me the value back. Remember, every time I connect, let's see if we can do this again, and I give it encrypted flag, and then I'll wait a couple of seconds and give it again, it changes. It's changing because we're having a different input. So let's see if I can do this here. I don't know if I can do this fast enough. Oops. Oh no, that's not good. Let me get encrypted flag again. Somehow copy that. There we go. So I was able to type this in and send it in the same second, and it gave me back the same value. So this is what I'm going to look to do. I'm going to send us a message saying encrypt flag, take that back, and then send in a bunch of question marks followed by my guess and see if I can get that first character the same. Because again, it's just going character by character. So what I have here is a solve script. I'll put this up if you ask for it on a GitHub or something. So let's follow what's going on here. Once this thing starts up, there's no main function. It's going to fall down to here and create a bunch of question marks. So 28 characters. I'm on index 0, which means that I haven't, I'm going to keep my place in where I'm actually guessing in this. I'm going to read the line from connecting to it. Then I'm going to say, while there's question marks still existing in flag, we're going to keep doing this process over and over again. That process is first to define a char set, which can actually be done outside of our loop. It doesn't have to be in here at all. Inside of this char set, what we're going to end up doing is evaluating the flag. So the flag here is all question marks. We're going to split this up into a list. And then for our current index, we're going to replace that with a guess character from the char set. So what this is going to do is it'll take something like an input of AAA, and then it'll split it to a Python list like this. Okay. And then it will pick the index. Computer science people always start at index 0. So it'll take the first index and it will put it from the first character in char set, which is going to be an H. Oops. So replace it with H, A, and then A. And then finally, this line here is going to say join it into a string. So that's going to take HAA and just replace it like this. And it's going to send that value. And it's going to do this over and over again. It will really, really fast. Okay. So once we have that, we're going to say trying flag, and then we're going to send check char. Check char is going to do a few things. First of all, it's going to send encrypted flag with a new line to get back what the current encrypted flag is for this timestamp. Then it's going to put that representation. This here is a very Pythonic way called list comprehension. It essentially packs a lot of things into one line. All it's going to end up doing is take the output and splitting it up into 2 character sets in an array or Python list. Okay. Then what we're going to do is we're going to take the current flag that that we sort of have here or have defined called this flag. It's a global at this point. And we are going to encode it, send that data, and then we are going to read the line from the encrypted text, split it out again, and then we're going to check to see whether or not that information sort of matches. So we're going to check index to index to see if we've gotten close to what, or the exact match of what we're looking for. So let's watch this thing run, and maybe it'll make a little bit more sense. First thing, it sends the request for encrypted data, grabs it, and then very quickly sends back a guess. And then it keeps throwing it. And every time it gets that right, it returns either true or false. If it returns true, check char is going to print out what our current flag is, and then it's going to up our index so that we move on to the next one. So it's actually going to update our flag and then break out of this tight loop and then go into it again, right? So we don't finish out the character set. We start fresh every time. So right now we're starting to start work through this. So speed, and I think this next one's an underscore. So it'll say match and then give us a current flag, and it'll tell us what it's currently trying. So with every one line that prints out, 2 requests are being followed. And what it's trying to do is to hit that same second boundary. If it fails, it just retries that same thing over and over and again. So there's a lot more requests happening here than it appears. And again, this isn't fuzzing. We're intelligently trying to enumerate the challenge. So this is perfectly fine. If you put up something to just attack the server in a very tight loop with just garbage data, then that would be a problem. We would have to stop that. But this is totally fine. So I'm going to go ahead and stop talking and let the script finish. Okay, at this point, it seems pretty clear that this flag is going to be HTH. Speed makes it possible. We'll see it finish off here in a second. All right, so that is the flag. Everything ran and kind of leaked it out. So essentially what we're doing is taking the fact that the session key is limited, that not every single time that we connect does it change. A better way to do this would be every single time we connect, there's a nonce, which is a number only used once. And that nonce would be used every time it connects. We would update that. And we can mix it with some other random values to make it not guessable. Also check when a nonce has been used, and if it's been replayed, we can deny it or just drop it. These are ways that we can get around this type of attack. But in this case, we're just using the time, which has in the way that we used it, a granularity of 1 second. If it was like a millisecond or like, some higher precision, then yeah, we might be okay. It's really hard to tell. I think at that point it becomes like an arbitration problem with how fast you can get, how close to the server you can get, how many requests that you can possibly make in enough time. You might have to convert this to C, make it a faster process, things like that. So you get into really squirrely areas when you try to solve this by a speed problem, right? So in this case, I'll submit this, and it was correct. So not too bad. This ended up being a problem that I think just took reading the code and understanding what was going on and working through the challenge to try to solve it. So that's it for the crypto problems. I hope you enjoyed this series and look forward to solving the next challenge set, which I think is going to be reverse engineering. We'll see you then.